Hi everyone, I am glad to present our work, Ascetic. This is a joint work of Nankai University, University of Georgia, and University of Minnesota. As we know, more and more applications are leveraging GPU for graph processing. To support high throughput of GPU, data have to be loaded into GPU memory before processing. However, compared to the limited size of GPU memories, the graph datasets are significantly larger. Therefore, we usually have to partition the graph datasets and bring the partitions in many times during graph processing. On the other hand, the current PCIe bandwidth has only about 10 gigabytes per second, which is much less than the GPU computing capacity. GPU often have to be left idle and wait for the data transfer during the processing. Efficient data transfer in out of GPU memory for large graph processing applications has become a challenging problem. Most existing approaches using graph partitioning to fit subsets of the graph datasets in GPU memory. For example, we can divide the graph datasets into partitions PA, PB, and PC as shown here, and transfer uh, each partition when it is reused. However, because of GPU's memory capacity, each partition will be swapped out before it is reused in the next iteration. We find that each data partition has a lot of unused data because only a small percentage of the data are accessed in each iteration during the graph processing. In a simple experiment, we ran PageRank, which is a benchmark that does page ranking in web graph benchmark suite. In a 10 gigabytes GPU memory, it has a dataset size of 20 gigabytes, but the total amount of the data transferred is more than 1000 gigabytes during the graph processing. It is because data partitions are being swapped in and out constantly in each iteration. But if we select PA to be kept in a static region and stay there across iterations, the data transfer can be reduced by 26%. It is because the partition PA will be reused across iterations. Based on this observation, we can conclude that exploiting data reuse across iterations can indeed reduce data transfer and improve overall performance. We also need to explore the access pattern of graph processing and take advantage of the data reusability across iterations. To explore data access patterns, we keep all vertices of the graph in the GPU memory and all its edges in the unified virtual memory on the CPU side. We then collect the edge access traces using NVProf. We divide the datasets in the chunks, and each chunk has 4 million edges. The x-axis and y-axis in the figure are the time and chunk IDs. We find that all access patterns exhibit a roughly sequential scan pattern. Because the memory footprint is larger than the GPU memory, most chunks has long reuse distance. The bottom figure shows the access count of the chunks in one iteration. As shown in the figure, almost all the chunks have been accessed, and the accessed counts are roughly the same. There appear to be no hotspots in the memory accesses during the graph processing. We also count the average number of access data in each iteration. It shows that the number of accessed is quite small in each chunk, and the access patterns are mostly random and sparse. We can thus conclude that the IRU policy is not suitable for graph processing, and each chunk in one dataset has roughly the same reusability patterns. We can pretty much select any partition and keep it in a GPU memory region called static region in our paper for cross-iteration reuse. For more details, please refer to section 2 in our paper. State-of-the-art schemes such as Subway put forward a fast subgraph generation technique, different from loading the entire dataset into GPU memory. It can quickly extract a subgraph from a standard CSR formatted graph dataset based on the specific vertices and transfer it to GPU memory to each iteration. We find the accessed dataset in each iteration just needs a very small portion of GPU memory. It also shows that only a very small portion of GPU memory is accessed in each iteration, and there is an opportunity for us to use a portion of the GPU memory to keep some data to be reused across iterations. Based on the above observations, we propose a partitioning framework called Ascetic. In Ascetic, we partition the GPU memory into two regions and store the graph data in each region based on whether they are to be reused or not. Most superficially, we fill the static region with the data to be reused across iterations, and the data to be used on demand in each iteration are stored in the on-demand region. There is a bitmap to keep track of the data stored in the static region, and the data not in the static region are loaded into on-demand region in each iteration as needed. After sending a request to CPU, Ascetic will reorganize the on-demand data on the CPU side and transfer the data to the on-demand region. For more details, please refer to the section 3 in our paper. The design of Ascetic has another benefit. In most existing schemes, CPU and GPU have to work alternatively, which means CPU and GPU have to be idle in turn. The partitioned memory in the Ascetic provides an opportunity to overlap the data processing by GPU in the static region and the loading of the data into the on-demand region by CPU. Thus is, in each iteration, GPU can start the data processing with the data already available in the static region, while simultaneously transferring the required data from the CPU into the on-demand region. It can significantly reduce the idle time on CPU and GPU. Other optimization is done on the data replacement in static region. The reusable data in static region can change over time and become stale after some iterations. To keep the reusable data fresh in static region, we need to replace the stale data in the static region when GPU is processing the data in the on-demand region. As the figure shown in here, we use a simple mechanism to divide the graph dataset into 16 kilobytes blocks. For each block, a counter is then to be record the number of accesses to the block. If the counter is below the threshold, it means the block has become stale and it will be swapped out. Again, please refer to section 3 in the paper for more details. Now let's look the performance. The figures shows the speed ups and the amount of data transferred of Ascetic over state of the art. On average, Ascetic achieves 2 times speed up. As the figure shows, the average amount of data transferred in Ascetic is only about 40%. We can see that the reduced amount of data transferred clearly corresponds to a degree of improvement in the overall performance. Unified Virtual Memory was introduced by NVIDIA in 2016. It provides an easier programming interface to deal with memory over subscription by using demand paging. Compared to UVM, Ascetic is shown to be 6 times faster, and the amount of data transfer is reduced by 73%. This is because, first, the smaller size of the page in UVM increases the frequency of the needed data transfer between CPU and GPU. Secondly, the long data reuse distance hurts the LRU-based replacement policy used in UVM. Thirdly, page fault handling in demand paging can incur high overheads. In conclusion, we explore the potential of data reuse in the large-scale graph processing workloads that usually over-subscribe the GPU internal memory. We propose Ascetic, a novel graph processing framework that exploits temporal locality across iterations by partitioning the GPU memory and improves the GPU efficiency by maximizing CPU and GPU concurrency. We have implemented a prototype of Ascetic, and it shows that it can achieve an average of 2 times speed up over a state-of-the-art graph processing scheme, and can also reduce the amount of data transfer substantially. Thank you.